Swayam Prabha. Digital India. Educated India.
I know this spherical coordinates is a little involved, but if you understand the spherical coordinates, then you can follow any other thing very easily, because this involves the linear dimension as well as angular dimension. And then understanding, there are two things which we need to understand here is the relationship between the coordinate axis. So here, though we say r theta phi, but it's really the unit vectors are er, e theta, e phi. So these unit vectors are obviously in the direction of increasing r, increasing theta, and increasing phi here. And the other ijk are the other things. So to get a relationship between these things, we discussed it a little last time. So I'll put it just to emphasize some of the points here is that so the unit vectors, wherever they are, they can be drawn parallelly here. For example, this P, which is in the ground plane, and as the projection of P here, as P moves with P increasing, so that means that this P prime goes along the circle of, if this is R, this is R here, and so that means that this is the direction E P. And so similarly here, E theta, theta is in the direction of theta increasing. So this is in a kind of vertical plane here, where P will be moving in the vertical plane with a circular radius of R. Okay, so you should try to imagine, and sure, you can do that. So the relationship between the coordinates is this one. And I'm just putting quickly here. So the finding out the relationship between ijk and er, e theta, e phi is that these are still not in terms of er, e theta, e phi. So let's put it, let's say this is just for the sake of, so there's a small delta 1 and there's a delta 2 linear dimension. So if you take a small linear dimension, delta 1, that's very clear. And in E theta, we call it as delta 2 and delta 3. I don't want to call it as delta theta because we already have delta theta here. So to convert this one into this one, so what we do here is, say, let us say I write delta 1 here, delta theta. So if I want to write it in terms of delta 2, so delta theta here, a small increase in the angle for delta theta, is nothing but a delta 2 divided by r. So that will constitute delta theta here. And similarly here, so this delta 5 which is there and which we represented as by a small quantity delta theta. So if you want to convert that delta theta here, so that should be, so that means that the same delta theta will be here, delta 3. So that means that if delta 3 is there, so the corresponding increase in delta phi is nothing but delta 3 divided by, how much is this distance? So this distance is r sine theta, right? So here I can write theta. So these angles are now converted into delta 1, delta 2, delta 3 because we need er, e theta, e phi here. So to do that, so what we do here is that we will take these things inside. So this R, if I take it inside, so this column should be divided by so I just want to write delta 1, delta 2, delta 3. So this is equivalent to the direction of, and here, so this R if I take inside, it will become cos theta, cos phi, and this is cos theta sine phi, and here minus sine theta. And here our sine theta will be taken and divide the third column here as now minus sine phi and cos phi at 0. So these are now exactly the way almost which we want it here. So these are the small linear dimensions, okay, when this P moves by a very small quantity, and if P moves by R theta phi, delta R, delta theta, delta phi, so the effect of this one is given by this matrix here. So this is nothing but our transformation matrix. So instead of writing delta x, delta y, delta z, and delta 1, delta 2, delta 3, we can equally write it. So that means that this quantity, for example, is nothing but if there is a change in the R, so what will be its corresponding change in the x direction. Okay, so that means that I take k. So this also can be written as so you call it as A, and here instead of delta 1, I'll write ER, E theta, and E. Okay, so this is the relationship between the unit vectors in R theta phi directions and the corresponding Cartesian components I, j, k. So wherever you find a vector, okay, with ER, E theta, E phi, you can convert that all those components by pre-multiplying with A. So if you have certain components here, and you can correspondingly find out what is its Cartesian components by using this transformation matrix. So this is a very general rule which you will apply it wherever you find a transformation. So as I was telling, so that means that the components of this ER in terms of I, so these are the ones, and similarly the second column components of E theta in J, and the third column corresponds to the components of E phi if there is a unit vector in terms of I, J, K. So interestingly, so these are all orthogonal transformations, and so if you want to write here, so I will, if I want to take an inversion here of this is what I also told yesterday. So this A inverse, if you write this one, becomes A inverse. But interestingly, so since these are the nothing but the components between cosine of the angle between corresponding axes, so that will continue to be here. They're exactly the same meaning will also come here. So that means that this A will become A inverse is nothing but A transpose. So this is whenever you have a triad vector here, which are orthogonal to each other, and then if you transform them from one coordinate system to another coordinate system, so you use this and the same A inverse, which is nothing but A transpose. You can also see very interestingly, you can do a double multiplication. Okay, so then definitely then you can see as this is going to be transpose itself. Okay, I removed this. I would have kept it. Okay, so now yesterday we were towards the end, we were looking at the how the expressions for velocity will be there. So that we'll have, say, starting with the position vector r, so which we represent by r, the magnitude, and the direction is along er. So if you want to find out the velocity here, dr by dt, so it's nothing but r dot er plus r dr by dt. Okay, so this is, so we can see this part is of course how the radial vector is increasing its the length r, so then you will have r dot. Apart from that, since the particle is moving, and if it's moving so that all the r theta phi are going to change, then what happens is that the direction of er by itself will be changing if there is, let me just draw it again, I'm sorry. Okay, I should have kept. Okay, so whenever this particle p is moving, so that it has a space motion, then not only is xyz keep changing, but even r theta phi change. But interestingly, if there is a change in the position of p, then this e theta, e phi, as well as er are going to have a change in the direction. Okay, so once they have a change in direction, magnitude may not change, but they have a time derivative. Okay, they have a small delta r will be there, delta theta will be there, delta phi will be there, and then there are going to be a time derivative for e theta, e phi whenever there is a change in the position of p itself. So if that's going to happen, then so any vector, so for example here, any vector here, even a vector r, if it is going to undergo, we have shown that any vector r under rotation, small rotation, or we say angular velocity, I'll put it as omega cross, then we say that the or correspondingly the theta, I think I'll leave that enough. Is going to be a cross product of, if it is just going to have a rotation under angular velocity omega, so then the particle p given by r is going to have a velocity component omega cross r also. So that means that it may be moving with along the direction of r, but just because it is having a rotation, so then you have omega cross r. So that's the same thing here. er here is obviously going to have let me say a delta er under what kind of rotations is going to experience? So the rotations are due to theta dot and phi dot, right? So this theta dot and phi dot, so obviously are the magnitudes, but they also will have the direction. So let's say just see what is this theta dot and phi dot. So together we can represent both of them. So if you have a theta here, and if you're going to just imagine that the theta is going to increase. So if theta is going to increase, then let us see first, maybe the simpler one, phi. If phi is going to increase, so then it is the point P prime is going to move along the horizontal plane. And what is the direction of the axis? So if it is going to rotate like this one, so z is the direction of angular velocity. So because it's going to rotate like this one, so z. So that means that we'll put it as phi dot k. This gives the magnitude phi dot as well as the direction k. On the other hand, so we also have a velocity due to theta changing, so theta dot. So if it is changing, so theta is increasing like this one. So if theta is going to increase, then so that means that what is it going to do? So it is, only imagine that this particle P is moving such that only theta is going to change. So that means that phi is constant, but theta is going to change. So that means that the P is going to move in a vertical plane. You can see it's a vertical plane because phi is not going to change. So that means that if it is going to move in a vertical plane, okay, rotate it like this one, and what will be its direction? So this direction is perpendicular to the plane of this vertical plane. So this is the direction of theta dot. Okay, so this is the direction of theta dot. And can you say what it will be? So it is going to be in the direction of E phi. E phi is a unit vector perpendicular to this plane. So you have a plane here in which E phi is exactly perpendicular to that. So that is the direction in which theta dot will be. So that is then, so it will be theta dot. What is the direction? E phi. So, and of course, R will be changing, but there's no angular velocity associated with changing R. So if it is just moving along increasing R, so it's not going to change anything. Okay. So this is omega. And so now what we have to do here is that this dr by dt, so this quantity is nothing but omega cross er. Yeah, right? So that means that this is omega cross. Interestingly, so this is what we had to put, phi dot k and theta dot e phi taken cross product with er, right? So this is the interesting part here. But it's a mix of the unit vectors. So some are in E phi, some are in K. Okay. So one of it should be converted into the other. But essentially, let us put everything into the spherical coordinates. So this K, if you look at this matrix A, okay, so the last column here, K, if you recall, so that's nothing but the last row here. It's written as cos theta r minus sine theta e theta, right? Right. So this is how k can be converted to er and e theta. So this k should be converted to this one, and this expression should have a cross product with the er, and then substitute back into this one, okay, into this one. Okay, so finally, if you substituting this here and taking a cross product with the R, so remember that this right hand multiplication rule, or what is the order? So this R theta phi. So this is ER and E theta, E phi are the and order. So in the sense that if you multiply ER E theta, you will get E phi. E theta cross E phi will be ER, and E phi cross ER will be E theta. And that's how you should take the order. Okay. So now everything is taken care. So if you take V, then R dot ER, that continues to be the same. So R times DER by DT. So DER by DT is nothing but this cross ER, and everything can be, okay, simplified. And let me give the expression directly. Okay, so you can do the cross product and all that. So I'll just give you, therefore, okay, substituting all these things. So we get R dot ER plus R theta dot E theta and R phi dot sin theta E phi. Okay, so this is the expression for velocity. So if the R theta phi are given as functions of time, then you take the derivatives here, R dot ER and R theta dot E theta and R phi dot sin theta E phi. So this will give you the velocity expression in spherical coordinates. The going to acceleration for acceleration. So acceleration is dv by dt. Okay, so that means that now you have to take each of these expressions. So that will become R double dot ER, right? And R dot d dt of ER, right? And then this R theta dot E theta, we can write R dot theta dot plus R theta double dot E theta. Sorry, there's one more term. So R dot theta dot and R theta double dot, and this multiplied by E theta, plus here we'll have R theta dot d E theta by dt, right? This is for the second term. And for the third term, we have three terms: R dot phi sin theta. This is the one we are taking time derivative of the first scalar terms. So R phi double dot sin theta plus R phi dot cos theta dot. So this is for E phi. And then we have to have, these are all very messy, but it can be done. Okay, so everywhere we have differentiated this first and kept this as it is, and then we took the first term as it is and we took the differentiation with time. Okay, so this is exactly will follow whatever we have done it for velocity. So having omega there, so what we have here is that d er by dt if you want. It is nothing but omega cross er, and d e theta by dt is nothing but omega cross d theta. Okay, so this is what you have to do. And finally, I'll give the final expression. So it's going to be a little, can be done. Whatever omega is there, you use that and take cross products with that. And everywhere you substitute, simplified. And finally, the acceleration equation for, so it will be r double dot r phi dot square sine theta. So collecting all the terms, this is the radial component, and we have r theta double dot to r dot theta dot r phi dot square sine theta cos theta theta. I'm writing these things so that you can use it if you need it. 2 r dot phi sine theta in theta 2 r theta dot phi dot. Okay, so it's long, but we are able to complete successfully. Okay, right? So I gave very slowly, very systematically how we can achieve the velocity and acceleration expressions once you have it in the spherical coordinates. So
Because they always stupid idiotic.
sorry, yeah. You want to say something, Fiber? Okay. I know. Please keep this in your notes. So there's only one small thing which I would like to tell you is there are slightly different conventions. I think I'll just mention the slight different conventions are, this is the usual convention for spherical coordinates. So this is what I followed. So where x is the Cartesian coordinates and point P has the distance r, and so this is the one which I used. And there is also another slightly different convention. So in which case, so this is taken as theta. So this is another convention. There's a slight change. So here we call it as theta from the vertical to the radial line, whereas here theta is measured here as x-axis to the projection of P on the horizontal plane. So that they called it as phi, and phi is the elevation, angle of elevation here to R from horizontal plane, whereas here theta is measured from this one. So accordingly, what happens is that So this is ER, and P is increasing this way, and this is okay. So the three triad R theta phi, ERE theta phi will look like this one, whereas here they look like this one. So this is Merriam did not give you a detailed thing, but he followed this one. He just gave some expression. So please be careful, whichever. So what's going to happen? So if you want to go from this expression to this kind of representation, what you need to change here is that this theta here should be replaced by 90 minus phi, and this phi has to be replaced by theta. Okay. So if you do that, so this theta here will become 90 minus phi, and this phi will become theta. Okay, so this is the how whatever expressions you have here, you can slightly change. So, well, people have different conventions. So, see which convention you are following. So, it's very important. Okay, yeah. This one. Yeah. Yeah, you're right. Yeah, please. Yeah, thanks. So there is a, I forgot, there's a square term here, please. Yes, there is. It's sine square. Okay, a little bit of algebra. So you have, I mean, quite a bit of algebra. So I wish that you start from the fundamentals. Maybe you can start this one as an exercise. Take this Merriam's thing from the fundamentals, theta phi, get an expression for x, y, z in terms of r theta phi, get the relationship between ijk and ere theta e phi, and then get the expression for velocity and acceleration. So please do that. That's a nice exercise. I will take up a very, very small problem. And you have some problems that need to be done in the tutorial today. And a little, I looks simple, but then trying to understand the axis and trying to, this is one example. Okay, so this is in an airport here, and so there is a radar here at this point, and this is, let me try to explain the axis here. So this is the vertical axis, and this is x-axis, and this line is drawn perpendicular to this projection of this plane. So this plane is taking off at 30 degrees at this point. Okay, and then it is steadily climbing at 30 degrees. So by the time it came here, so the height is 600 meters. So this observation horizontally it is 2000 meters away, and this is the vertical line. So this is the vertical axis, and then this is the one going in the vertical plane. So this plane is going in a vertical plane. Okay, I hope you can understand this one. And so what is given here is that velocity is 500 kilometers per hour, which you can write it as 138 meters per second. What is asked is that what is the distance r dot. So if this is r and theta dot, I'll tell you what these are. When the plane is at P exactly, opposite line. Well, opposite is a little difficult. So this is the path on the ground as the plane is moving, but however the plane is moving at 30 degrees. So its projection is along this line, and then while it is at this P, which is at 600 meters, so what is the, when you have a radar here, so what is its tracking? So we would like to find out how this range R is increasing or decreasing, and what is theta here. Theta is the angle here. This angle is theta, and let me tell you that this is the angle phi. What is angle phi? So in general, if you have a p and p prime here, let me say that this is q maybe, when plane is at q. Let me just differentiate between p and q. So p is a general point as the plane is moving. So if you take its projection on the ground, and then if you join to the origin, so the angle between x-axis and to that projection line is phi. And while theta is, so let us say here, so what is theta? So theta is nothing but, if you join this r, so this r vector, so the vertical to the vector r is theta. Okay, so this is the usual theta, r theta phi is our usual coordinates. Okay, so if these are the usual coordinates, so we would like to find out the velocity in terms of this r theta dot phi dot. You can also find out acceleration. So let's just see. Okay, so what is interesting is that the velocity given here is what? So the I and j, so this is I, j, and if you draw the ijk here, so I is parallel to x-axis, k is in the vertical axis, so that's z direction, and j essentially is along this line. Okay, so that's what ijk are. So j is parallel to, so this is the y-axis. Okay, so that means that the velocity here, if you want to write, so the velocity is along this line. In fact, you have to find out this angle. So let us say alpha. So this alpha is, let me just write here. So alpha is tan inverse 600 by 2000, and this about 16 degrees, and the distance r at this point is okay. So if this is alpha, okay, so then we can also find out phi at this instant is theta. Sorry, theta at this instant is 73 point. So this angle is 16.69 degrees, but from our vertical reference line is 73.31. So using this, so we can find out. So that means that this is okay. So essentially the velocity here is, so plane is moving in a vertical plane. So if you take that vertical plane, so essentially the vertical plane here is xz plane. And so velocity can be written as v cos 30 in the I direction and v sin 30 theta. So this can be put as 120.2 I okay. So that's in terms of, you got it in terms of I and j coordinates. But essentially what we require is r theta phi and r theta phi. So for getting this, the transformation, so we know that ijk components. So I gave you the a here. So a expression is there. So in where we have what at the point q, at q, that theta is how much? Theta is, we found out. So theta is 73.31 degrees. And what is phi? So along this line at q, so phi is going to be 90 degrees. So phi is going to be, and r, anyway, we have it. So r is 2088 meters. So once you have that, so we can have a, given expression for a. Yeah, the expression, if you put all those things, so it will turn out to be 0, 0, minus 1, minus 9.5, So this is, if you put it in that cos theta and sine phi and all that, so that's what you got, A. So this is for A. And what is it which we need? We need to transform x, y or ijk into er, e theta, e phi. For that, we use the inverse of that. And for that, we have er. Maybe I'll continue here. Don't mind. Just for it's almost done. I'll continue it here. So er, e theta, e phi. So this is nothing but your A transpose I J K. So if you have I J K components here, so then, so what are I J K components here? So this is for the velocity here. And so we have, so this one, if you write it, so this is, if you call it V cos 30, and that's 120.20 and 69. So in which case what we get here is VR, V theta and V phi. So this you will get it as 19.93 minus 66.47 and minus 1. So what almost done. So what we also have the expressions for VR, V theta. So we have the expressions for VR as R dot. V theta, we have the expression for R theta dot, and V phi or phi dot sine theta. So using those magnitudes and using these expressions, so we get R dot as 19.93 and theta dot as 0.3644 and okay, so this is how we can solve. Yeah, so this is how we make use of the transformations and make use of the expressions, and then we can convert. This is an exercise of converting Cartesian coordinates into polar coordinates and vice versa, and also looking at the expressions for velocity and acceleration. Okay, I think I'll leave it here. Please do all these things. These are a little long expressions, but once you understand how the transformations take place, so you will be able to, you should, well, why you will be, you should be able to transform and analyze the motion in spherical coordinates.